One of the first steps in designing a scientific experiment is determining what technique to use. There is often more than one option, and different techniques will have different advantages and disadvantages. For example, Onondaga Lake is heavily polluted. Imagine that we go to an Onondaga Lake and collect some water from it, and we decide to determine what the benzene concentration is in this water sample. How would we make this measurement? Well, there are a lot of options. For example, we might extract the benzene and weigh it. We could use chromatography or spectroscopy, or perhaps some other techniques. Each of these methods will have specific advantages and disadvantages. For example, we'd have to have a lot of benzene to be able to weigh it accurately. So perhaps this first option is not a good one and can be discounted. Some of the factors that we consider when determining which technique to use are the sensitivity of the technique, its practicality, and its cost. Sensitivity means, as it sounds, how sensitive is the technique? How low of concentrations of benzene can we measure, for example? One question of practicality would be access to the technique. Do we actually own the instrument that would make this measurement? Cost is often a factor because some techniques are much more expensive than others. In this week's experiments, we will compare different techniques used to measure the same property. One technique that we will look at is absorption spectroscopy, which we'll use to measure the concentration of an analyte. Absorption spectroscopy occurs, or can be used, when a molecule absorbs a photon, which is denoted as hν. After absorption of a photon, the analyte is excited, either rotationally, vibrationally, or electronically, and this is denoted by the asterisk beside the benzene molecule drawn on the right-hand side of the equation. In this week's experiments, we will be exploring electronic excitation. Electronic excitations occur when molecules are irradiated with light in the ultraviolet and sometimes visible regions of the spectrum. This is why we often refer to UV visible or UV-vis spectroscopy. The degree to which light is attenuated is referred to as the absorbance, and it is given by the equation A equals epsilon BC, where epsilon is the molar absorptivity, B is the path length, and C is the concentration. These concepts are discussed in more detail in your pre-lab reading. Here is a schematic showing how absorption spectroscopy works. Light is passed through a cell that contains the sample and then reaches a detector. Transmittance is measured as the fraction of light that reaches the detector in the presence and absence of the analyte. The absorbance is negative log transmittance, or log I0 over I. And again, this is discussed in detail in your pre-lab readings. In the absence of an analyte, a large amount of the light may pass through the cell and reach the detector. This will not generally be 100%, as discussed in your pre-lab readings, but for the sake of simplicity, in this example, we say that all 8 photons that pass through the sample cell reach the detector. So in this example, I0 equals 8. Now say we replace this cell that has no analyte in it with a cell that has some analyte in it. Now when the light reaches the cell, some of it is absorbed. So only 3 photons reach the detector. So I0 was 8, but I is 3, and absorbance is given as log 8 over 3, or 0.43. Now this number becomes useful for us when we combine it with the first equation that we looked at, A equals epsilon BC. And we can rearrange this equation to solve for concentration. Now we have just measured or calculated absorbance, and we can look up what the molar absorptivity is. So say that our photons were at 254 nanometers. We could look up that epsilon is 200 liters per mole per centimeter, and we can know by measuring that our path length is 1 centimeter, and that is the width of the cell. So we plug those numbers into our equation, and we determine that the concentration of benzene in Onondaga Lake water is 2.1 times 10 to the minus 3 moles per liter. So absorption spectroscopy is a simple and effective tool for measuring concentrations of analytes, either in the gas phase or in solution. Fluorescence spectroscopy is another technique that is commonly used to investigate physical and chemical properties of molecules. Fluorescence is initiated by the absorption of a photon, as discussed before, which is followed by the emission of a photon. So an excited benzene emits a photon to return to its ground state, and we can measure the light that is emitted, which is called fluorescence. Fluorescence generally occurs at longer wavelengths than absorption. So for example, benzene absorbs strongly at around 255 nanometers, but its maximum wavelength of emission is 285 nanometers. So energy is lost between absorption and emission of a photon. Let's compare absorption and fluorescence spectroscopy. So an analogy to absorption spectroscopy is that 200 people gather in a dark field and they all have flashlights on. Now when our analyte absorbs light, some of the light goes away. So for example, you say, tell 20 people to turn their flashlights off. It's hard to tell that anything happened. There is such a large background that a small change is hard to detect. Absorption spectroscopy, for this reason, is a very insensitive form of spectroscopy, so you can't necessarily use it to measure very low concentrations of analytes. Fluorescence spectroscopy, on the other hand, starts out with a dark background. We still have 200 people in a dark field, but all of the flashlights are off. Now we will say, let's have some fluorescence, so let's have 20 people turn their flashlights on. Well, that is something that is very easy to see. So since we have pretty much no background for fluorescence, it's a very sensitive technique, and sometimes it can be used to measure concentrations that are orders of magnitude lower than absorption spectroscopy. So given this information, we might think that fluorescence spectroscopy is always the better choice than absorption spectroscopy. However, all molecules absorb light at some wavelength, but not all molecules fluoresce. So while fluorescence is more sensitive, it is also more selective. So it isn't as widely applicable as absorption spectroscopy. So different techniques will have different advantages and disadvantages, and these must all be considered when determining which one to use to make a specific measurement.